This short video is going to show how to use the cut up and sum up method to create an integral formula to calculate a quantity of interest. In this case, it's going to be the area between two curves. So for this example, we're going to let f of x and g of x be continuous on the interval from a to b. And also, for the sake of this example, we're going to suppose f of x is less than g of x for all x's on that interval. So the picture associated to this would look something like, we've got our x and y axes, we've got our interval from a to b, and we're going to have our graphs of our two functions, f and g. So f might be here, and g of x, its values are larger than those of f of x, so its graph is going to be above that of f of x. And so the area we're interested in is this one, the area between these two curves on this interval. So what I'm going to show in this little video is how to derive this formula for this area. And the formula is an integral formula. The area is the integral from a to b of g of x minus f of x. That's the integrand dx. Let's draw our picture. Start with the coordinate axes. Here's the x-axis and the y-axis. And then our graphs of our functions. So here's a graph of f. Let's say here's the graph of y, or g rather. And the interval we're working on, interval from a to b. And so here's the region of interest. To do the cut up and sum up method, first we cut this interval up into n equal subintervals, and that divides this region into n strips of equal width. So let's write down n here. That's the number of strips, number of subintervals. Then that gives us the width of our subintervals. Okay, the total length of our interval is b minus a, and so dividing that into n equal subintervals gives us delta x as the width of each subinterval. So I'm going to write down a symbol representing those points on the endpoints of the subintervals. So xi is going to be a plus I times our delta x. And here, I is an index. It starts at 0, goes up by 1, 1, 2, all the way up to n. Now, if you notice, plug in 0 for I, so x0, that just equals a, because this disappears. So a here, that's x0. Likewise, if you plug in n for I, xn, if you work this out, put an n in here, and put this formula in for delta x, you'll see xn is just b. Let's put in the partition points, the xi, so this would be x1, this would be x2. If this is xn, this one here is xn minus 1. And let's just label these here generic points, x sub I minus 1 and x sub I. All right, so I'm going to let a sub I be the area of the ith strip. That is to say, each of these partition points slice our area of interest. And each of these is a strip. So the area of this strip would be A1, the area of this strip would be A2, and so on until we get down here to area AN. Okay. So let's here look at the ith strip right here. Okay. So that's going to be this strip. Its area is A sub I, but we can't calculate that area. We don't have a formula because the curviness up here. So we're going to approximate the area of this with using a rectangle. So the rectangle I'm going to use is this one. Okay. It has width delta x, because that's the width of the subinterval that created it. So the question is, what's the height here? Well, this height is given by the function g, and it's at xi. So that's g of xi. And this height right here, that's given by the function f. That's f of xi. So this height of this rectangle is g of xi minus f of xi. So we can calculate the area of this rectangle, right? And the area of that rectangle, which is approximating the area of the strip, is g of xi minus f of xi delta x. We know the total area of our region is equal to the sum of the areas of the strips of the region. We also know that each of those strips, its area is approximately equal, here's our approximation, equal to the area of the rectangle we're approximating it by. Okay, so here comes the calculus. Now, take the limit as n goes to infinity of this stuff, both sides of this expression. So the total area, that's just a constant. So the limit of a constant is a constant, so that is unchanged. Now this approximation, because of the way the rectangles approximated the area of each strip, the differences become really small very quickly, so that approximation actually becomes an equality. And so here's the limit of the right-hand side. But this here you'll recognize as a Riemann sum. And with this limit in front of it, this is exactly the definition of a definite integral. Hence, we've derived a formula for the area between two curves and given it in terms of a definite integral. Ta-da.